Hi all, welcome to the latest in our series of technical webinars on just some of the exciting new functionality introduced in Vulcan version 10. Today we're going to focus in on new capabilities available to those using in stratigraphic deposits, and going to have some functionality for the geologists and some for the engineers. Before we get started, just some brief introductions. My name's Peter Odens from the Maptek Sydney office, and I'm product manager for the Workbench in Eureka, but also heavily involved in ongoing stratigraphic development in the Vulcan software package. And James McKenzie will be joining us too. He's one of our senior technical engineers from the Vulcan Technical Services side of things, and he'll be talking to us about the open pit solids options. A little bit of housekeeping. This session will be recorded, and when it's done, you'll be sent a link when it's all edited up and you to have a look at yourself and share amongst your friends. And also in the little interface you have in front of you, there's a question box, so please feel free to type in any questions you think of as we go along, and we'll do our best to answer all of them at the end of the session. Okay, so what I'll do is I'll flick it away over to James, and he can talk to you about the new open pit solids option.
Thanks for that, Pete. Okay, so in version 10, we decided to streamline the reserving side of things and how we go about it. So we put the feelers out amongst you guys to see how you went about doing it in Vulcan, and then tried to streamline that process as much as we could. And what we came up with is this new menu option here, Open Pit Solids. Okay, so what you'll find in Open Pit Solids, I'll start with the split pit setup and then explain to you the rest of the options here. So this split pit setup, the whole basis of this is taking an overall pit solid triangulation and then splitting it up into horizons, strips, and blocks. Reserving the solid triangulations and then attaching those reserves back into the solid triangulation as an attribute for you to take on further. You need 4 ingredients for this to work. So as I said, first of all, you need the overall pit solid triangulation, which we can see here, which ideally extends up above your top horizon and below your bottom horizon. We clip those out in the process. We also need some strip lines, so they can be either 2D strip line, as I'm using today, can also be a benching and battered projected strip line, or you can also use templates, triangulation templates, which you've created by manually projecting your own strips through your horizons, or adding in ramps, however you want it to go about doing it, triangulating your strips, and we can add those in. You also need straight block lines. The blocks can also be triangulations if you have a funky setup with your blocks as it moves up through the strata. And the final ingredient is your horizons, so that they have to be grids. So in this split pit setup, we can call on a specification file. I've got one set up here. This first branch here on the mode, you can tell it how you want to go about doing it. So in which order do you want to split up your horizons? You can start with just using your strata grids and then break it up into benches if you want to mine it in benches, or you can split it up initially in benches and then add in your strata grids and split it up that way. Moving down to attributes, so we have our attribute identifiers. So this is what they're actually going to be labeled as when they get attached back into the solid triangulation. You can also choose to create some or calculate some attributes on the fly as it creates the solid triangulations. So you can see here we've got things like average thickness or vertical thickness. You can turn these on and off depending on whether you want them there or not. It also breaks the solids down into material types. So you can create overburden material, mid-burden, and we've labeled this as product. And the reason why it's called product is you're not limited to just using this within the coal environment. It can be any stratigraphic reserve. Moving down to the equipment, you can attach equipment into the material type. So if you're going to be using this moving into your scheduling package, You can attach bits of gear to the solid triangulations as well. We've also decided to add in a basic projection macro panel here. So this allows you to, if you're just trying to get some quick numbers out, you can come in here and create a real basic projection. This is what I'm going to use today. But as I said, you don't need to use this particular panel if you've already done your projections using benching and batters, or you've created your high wall templates. In this case, I'm just using a coal batter of 90 degrees, mid-burden 70, overburden 65, and a 20-meter berm on the floor of coal. Moving to the horizons branch, on here you can call up any horizon spec file that you've got. So in this case, it's a BB spec file taken from benching and batters. You can also use a glob file, or if you don't have any of those, you can create your own horizons list here inside the panel. You'll notice here that they're all grids, all of the surfaces. At this stage, that's what we're using in this process, just to streamline it all. It will be in the future moving into triangulations as well. Okay, moving down to the strips branch. In this particular data set, I'm just going to use some 2D strings here. You can see I've just created some strip lines that are offset from each other. Here's where you would select if you were using benching and batters strip lines. And as I said, you can tick on to use high wall triangulations if you've manually created templates. Moving down to the blocks here, you can use 2D objects, which I'm using just the straight lines to indicate your blocks. If you wanted to, you can attach the name of the block. So see, this is object 18, it's block line 18. You don't have to though, you can name these blocks manually down here as well. Okay, you can see at the bottom of the panel, it's starting to build how the solid triangulations will be named. So in this case, it's going to call it horizon underscore. You can change that sequence around as you want to. So if you wanted to call it strip first, you'd have square bracket strip underscore, however you wanted to do it. Moving down to the benches branch. So you can also cut your solids up into benches if that's how you want to go about mining. The benching panel is pretty flexible in how you go about doing it. So you can apply a universal bench, so say 10 meters, you take 10 meter flitches, 15 meter flitches, however you want to do it. You can vary your flitch heights in particular materials. You can choose to only bench in a certain material as well. So if you wanted to bench in your overburden only, you can just cut your solids up in the overburden to be benched. You can also choose to limit it to a seam type. So if you only bench within a particular seam, you can also nominate that as well. And once again, down here in the naming, you can see it starts to add in that bench number into the naming process of the solid triangulation. And finally on this panel here, we've got the qualities. So this is referring to how it's going to, or where it's drawing the reserves from. In this particular data set, I've just got some grids, and I'm just going to reserve the product, which is, in this case, coal. And here are my variables. Okay, so any variable grids that I've got, I can populate within this panel here. You can also choose to reserve from a block model. So if I've got a HARP model and I don't have the grids, then you can choose to pull any variable and reserve those out from inside the block model. Once we've got our selection there, just make sure that's all good, we hit apply and run. Okay, we come through into this panel here where I can tell it where I want all of my solids to be stored. So I'll just place them in webinar.try. Pick my pit solid name, and the beauty of this process is you can come in and out of it at any stage. So although it's kind of streamlined the whole reserving process that was otherwise fairly manual, you still have full control over it. So it's not a black box function. You can choose to start it and stop it at any stage, change whatever you need to change, and then continue on that process. So you still have full control. I'm just going to let it run all the way through here. So if we hit OK, first thing I need to do is pick my strip lines, give it a direction of mining, continue that. Now I pick my block lines and a direction of advance for my blocks, continue, and away it goes. So you can see there it's created my projection straight away and started the chopping process. So whilst it does that, I will come in here and we can have a look at, briefly discuss some of the other options here. So just below the split pit, we have clip solids. Now what these two options do, the clip solids and update solids, is allow you to update any of your split up solids without having to rerun that whole split pit process. So if you've run your reserves and then end of month rolls around and you have an updated topography, you can come in here, add your updated topo, pick your solids and choose to keep above or below the surface, hit OK, and it will re-chop all of those solids, only changing the ones that have been affected. So it's just a nice quick way of updating your reserve solids with a new surface without having to re-reserve everything. This option isn't just limited to the reserving solids either. If you, for whatever reason, you've got a whole series of solids, it might be, you've built a model of a dump and cut it up. You've got an updated dump. You can use this tool for anything where you have a whole bunch of solids and a surface that clips them and you want to keep above or below the solids. It will split them up and keep everything valid. Okay, the update solids is the next step in that process. So once you've updated your solid triangulations with a new topography, you can come in here to re-reserve them. Basically, it will recalculate all of the solids that have been changed with the updated qualities and attributes, geometric attributes. You can also use this process, so say if you run the split pit with your in situ block model and you want to reserve against in situ, but you also have a ROM block model as well, you can come in here to update solids and rerun all of those solids again with the ROM block model and any variables in the ROM model that you want, and append those attributes to the solids. So your solid triangulation can then have the in situ variables associated with it, as well as any ROM model or any other type block model that you've got, thus containing all of the information essentially. Okay, and the final one I want to discuss now is the export triangulation attributes. Okay, so this is one that allows you to basically pull all of those reserve attributes off the triangulations and into a text file. So if you were taking this information into a third-party scheduler, you can come in here and choose, you have full flexibility around which attributes you want to take, which triangulations you want to take the attributes from, and also how you want to format your text file to take into any other third-party packages. Of course, this will be made redundant when we release Epoch, which will be simple drag and drop for our solid triangulations as a reserving package. Okay, we'll jump back across here and we can see that it's already finished. Each step of the way it's telling me how many solids it created, and the final count is close to 2,000 solids. And down the bottom in the report window here we can see that the volume variance from the overall solid to the combination of all of the individual solids is 0%, so they equal out exactly. So we'll just remove that. Move these layers. You can see I chose to save my projections as a layer, and that's all the projection strings that it created. Hit save there. Okay, we can open up or expand down this .try folder where it's stored all the solids. You can also see as a byproduct, it keeps all of the solids that it creates as it cuts it up. So you've got your strip solids if you want to refer back to those. You've got your horizon solids if you want to refer back to those. So this is where I was saying you can go back to any stage in the process and change something and then continue on again. So we'll have a look at the block solids here. New feature in version 10 is we can filter these down. So if I only wanted to load out the coal, for instance, just underscore CO, and it filters these down, or OB. Whoop, maybe not. But in this case, we'll just load them all out and have a look. Okay, so there is my pit. And you can see it's made of all individual solids. If I hover over this particular one here, you can see all of the attributes associated with it coming up in the data tip there. And likewise, I'll go to Workbench and open up the property editor, expand down the attributes, and you can see, got an ash value there, British thermal, etc. Okay, so it's reserved all of those solids, and all of these attributes are attached to that solid triangulation. We'll just do a quick check to make sure that they are valid. Okay, we can see here in the report window that all of the triangulations passed the test, so they're all valid, which is good news. Okay, we'll have a look at the final option we have here in Open Pit Solids, which is this triangulation visibility. Okay, so this allows us to create any type of query to make our triangulations, or to view our triangulations on the screen. So I have one saved in here. You can save them, once you create your expressions, you can save them so you can call on them later. In this particular one here, I want to view all material that's labelled as product, so I only want to look at my coal seams basically. And down here, as well as, I've added this and, I want to view only the coal seam that has an ash value of 5, or larger than 5 and less than 15. So if I hit apply, whoop, go up here, that step gets me every time. Apply that, and okay. So we've thinned down to just our coal seam plies there in our visibility. Now, one other feature I'm going to show quickly is under this triangulation attributes, we can color by attribute as well. So in this case, I have a ash value there. So I just color my triangulations by ash. Okay. And just in case, we can bring that up and have a look. So that's about it, guys. As you can see, the process was designed to give the user the same amount of manual capability that you had before within Vulcan, but also streamlining the process to make it vastly quicker, which allows you to run more iterations and more scenarios with the data thus, fine-tuning your end result rather than spending all of your time just trying to get a result in the first place. So now I'll hand you back to Peter, who's going to look at advanced throw fault modelling.
Okay, thanks for that, James. So, as James has been mentioning already, we've listened to user feedback, and that obviously informs to a great degree what we put into our upcoming versions. And throw faulting, or faulting of complex stratigraphic deposits, we obviously did put in a solution to that way back in, and many people adopted it and are currently using it with great success. But there was feedback saying, well, in some instances it's actually quite difficult to create the mutually exclusive solid domains, and we don't need the absolute resolution on the fault plane, if you like, that block faulting gives you. So what we've done is enhanced the old throw faulting method. So if I jump into Vulcan here, previously you might have given it a bunch of solids. Now you can define your faults as a series of strings. And obviously you always could do that, way back to version 3 you could do that, whereby you could offset a grid vertically via a throw stored in the W tag. So we're still using that. So each one of these points has a throw. In this case it's in meters. It's tapering off to 0 at the ends, but it doesn't have to. And the sequence of the points, if I stand on the first point and look along it, it's going to throw up to the right if it's a positive value. So there's nothing new in that. But if you imagine looking at this and saying, okay, how am I going to break these up into individual solid domains? Especially with these sort of sub-parallel fault layouts, it's quite difficult, or little faults like this thing here. So rather than have to do that, we introduce a new method which allows you to have the throw encoded in each of the strings, but also the dip. So the dip itself is encoded in the point name. And you can now see each of the points can have its own varying dip. And that will allow Vulcan to generate a fault plane on the fly for you, and then use that to fault your deposit up. Now, Vulcan is very good at modelling large resource scale, sort of, industrial strength, if you like, coal deposits or stratigraphic deposits. What a lot of people don't realise is it's also just as good at doing small scale modelling, and that's really where something like this comes in to the forefront, because it's so easy to set up. This is basically it. If I have the strings in the wrong position, it's a CAD exercise to move a point. If I have the throw wrong, it's a CAD exercise to change the throw and to rerun it. Assuming I'm happy with this setup, to actually use it, we go back into the tried and true model stratigraphy option under integrated strat modeling. And for something that's a fairly major enhancement, there's not actually that much to see in the panel. Everything else you've used before, your extents and where you're getting your data files from, is the same. But under faulting, instead of setting up, say, a bunch of block faults here, we're going to go to the throw option now. Now, previous to version 10, you would have seen enable throw faults. And that would offset grids with a fault sort of propagated up vertically through the sequence, and no way of encoding any sort of angle on the fault. But now with this new option, we can actually put a dip into it. And as I mentioned, that can be on a point-by-point basis. So there's a few controlling options here. As we'll see in the output, the output of this is basically a triangulated grid, and you'll see the fault has been imposed within a sort of zone inside that surface. And this multiplier allows you to sort of determine, as a proportion of the throw, how wide that zone is. So if you really want the fault to go back a long way into your surface, then you can make that a bigger number. If you want it to be sort of fairly limited in plan, then make it 0. There is obviously a sort of standard way we define how these angles, what they represent. So in this case, I'm using an anti-clockwise from horizontal. So what that means is this string here I know is digitized from south to north. So if I'm standing on that string, imagine on the ground looking along it, and I've said if I look to my east, the horizontal, I'm going to flip that 120 degrees. So basically my fault plane, if you can imagine it, will be dipping downwards to the east. And it'll either be 60 degrees down from the horizontal or 120 degrees up, depending on which way you think of it. If you want to flip it, you can make that anti-clockwise instead of anti-clockwise. Okay. So by simply using that and the sequence of the string and the value, you can easily control which way your fault planes are going to go. And we do have a preview option on the planes too, so it's easy to check. So you can see here, some of these will be normal, some of these will be reverse, and it's very easy to change it if you make a mistake. In addition to that, we can then define, okay, I have a whole bunch of horizons here. Does this one fault string go through each of those horizons? Quite often that's not going to be the case. So you can define a sort of a sub-horizon list, if you like, a subset of all the horizons and say, okay, from C1 to C3 is faulted by that string. But I know that when I get down to the D horizons here, D1 to D3 might be faulted by a totally different layer, right? And so you can set up multiple entries in this panel here to define exactly which faults correspond to which surfaces. These things can actually overlap each other. And you don't even have to have a different layer. You can actually come down to the object level and set it up on an object-by-object basis if you want to. This reference scheme here basically says, well, these faults are no longer just vertical in terms of how they're propagated up and down through the sequence of your horizons. So as they pivot, you've got to tell it, well, what does it pivot around? These strings, currently the RL of these strings is irrelevant. It's the plan location that counts. So if I say that's referring to the C3, it's going to actually project that down onto the C3 floor and pivot at that 122, whatever it is, angle up through the sequence. And that's where that plane is then going to intersect all the other surfaces. If I don't have the information or the time or whatever to actually encode different angles on these strings, you can just give the entire string or an object within the string a overall dip angle. Currently this will be ignored because I do actually have values on the strings. Obviously having the ability to sort of twist the fault plane at every point gives you a lot more control over where it goes. If you want to, you can say, well, I've bought my own in terms of the fault planes. So don't forget, we're not talking about making solids. None of this involves making any solids. It's only a string exercise. But if you had gone and made yourself a fault plane and have the associated throw string, you could then say, well, rather than use the automatically generated plane, I'm going to supply my own here. And that can have whatever geometry you want to have with it. But for the time being, we'll leave it fairly simple. So once we have that set up, all the other options are pretty much standard ISM. So we can save this. Let's pop this out into another directory, test2. Let it run. So it goes and makes the planes, and because it doesn't have to actually make a totally independent stratigraphic model in every little individual fault domain, it actually runs a fair bit quicker because it has to only run it once, not 30 times or whatever that might end up being. So that's run, and I've run it over the entire area. So you see, for a start, it's thrown into this faultplanes.try directory the planes that actually created for me. So if I load those, you can sort of see this porcupine effect here of all the planes it's used, for instance, on the, in this case, the C3 horizon. So if you sort of look inside there and think we're trying to make solid domains of that, that would be a fairly difficult job. So this gets around all that problem. You can also, when I'm using this, run it on a single horizon and just create these planes and just check them to make sure you've got them actually flipped in the right direction. And if you haven't, just either reverse the option in the panel or change your dip angle very quickly. So you can sort of check this before you. Obviously, in addition to the fault planes, we have the actual faulted horizons themselves. So they have the same extension as a block faulted surface, but as you'll see, they're actually interconnected, so it's a single joined surface. So a reverse fault would look like a Z, and a normal fault would look like a stretched down S. So if we load those up, they have been automatically color-coded by a legend I supplied. Probably the easiest way to check them initially is to go into section view and just cut a section across them. Let's make this a bit narrower. So you can sort of see the interplay now of these fault planes, the green lines, and then the various horizons. And you'll see I've got some here are normal, being normally faulted, some are being reverse faulted, and you can sort of see if I highlight this, it's actually folding back on itself in a Z shape. If If I just drag the section through, you can also see how as faults come and go, their influence changes. So if you look at this fault coming in here, this surface has not been affected at all until that fault hits, and then it starts offsetting it based on whatever value I had there. And if we look at these actual strings, you can see the label, the dip label flashing up there. I could maybe change that. Let me just expand the view window a little bit here. I can maybe change the label on this to label that string by its, whoops, wrong one, sorry, by its throw. So that's saying it's roughly a 10-meter throw here, so I can check it very quickly. If I grab this from here to here, the blue surface, we're looking at about a 9.6, but I was pretty rough in picking it. So you can see how the throw is being sort of enforced into the surfaces as you go. If, for whatever reason I wanted to change that, I could actually edit it here, change that to be a 15-meter throw if I had my drill holes loaded up and weren't quite doing the right thing, and rerun the model very quickly to sort of iterate my way to getting it to throw the amount I want it to throw. Let's have a look at this in plan view. So I'll get rid of my spaghetti here temporarily. So if I load up a single surface, actually let's do the bottom one here. You can see if I wireframe that, basically where there is no additional faulting, it's just like a triangulated grid, and then where a fault has been imposed into it, you can see in this case it's a reverse fault, and it's actually been pushed back over itself. This one here next to it is another reverse fault. You'll see that they can, this is a normal one petering out to zero throw here. So it's a single surface with the faults imposed into them, and also that whole idea of the zone of influence, or the width of influence of the fault, you can sort of see here, because this is where the fault has been imposed into the surface. Now the beauty of an option like this is, like I said, Vulcan is not just this dinosaur package for modeling resource models. It actually is a very good short-term modeler as well. So if I bring my faults back in and I'm looking at this surface and think, oh, hang on, I might have missed a fault here. I'm seeing something maybe along here. So let's whack another fault in. So previously I'd have to go and, if I was just using block faulting, go and remake my fault blocks and go through the process of making them all mutually exclusive and valid. Now I can just put the thing in there. So I'm going to snap onto that surface, and if I look at the RL change here, I'm seeing that's 350 up there. That's 317. So I'm going to try and impose, whoops, make sure I hit the right option, into my layer, a new fault. Quickly, that sort of comes along here, goes up that face, and goes along to there. So there's my new fault string. I'll just remove that. So currently it has no throw, so let's sort that out. Object W, so very quickly I can come in here and say, well, I think this fault has a throw of around about 40 meters. Bang. And what dip angle do I want? Well, I think it's a reverse fault, so I'm going to go and change this and make the actual point name, I'm going to give it a dip of 120. Okay, and I can check that quickly by labeling that. There's my dips. So now if I save that into my layer, I can simply rerun using that new information. So let's just do that real quick. So you can see how easy it is to impose new information. If you've got CAD or whatever telling you where the fault strings are, just jump in there and use it, and you can make very quick short-term models. I can make the extent much smaller and the grid much tighter if I want, and throw out a nice new surface. So now I've rerun that, I've overwritten it. You can see in version 10 we get this blue colouring, meaning it's been changed. And if I drag the new surface up, you can see a brand new fault has been imposed into that model, very little effort. And I've guessed the offset reasonably well. I mean, obviously I've made it 40 everywhere, so it looks a bit strange, but I can change the throw. But it's that easy to impose your fault into the surface. And of course, once you have a whole stack of these surfaces built up, you can then go and create the heart model, and that then becomes input, as James mentioned, into the overall creation of your reserved scheduling solids. So the whole process, especially if we start using the version 10 workflow manager, has been made that much easier with the command lists to then guide the users through a quite simple CAD exercise to set up your strat model, do what if scenarios, get your grids built, make your hub, and then reserve it, and off you go. So in terms of the overall functionality of the throw faulting, that was pretty much what I wanted to talk about today. Just quickly before we have a look at the questions, we'll just say thanks for your time, both myself and James. We'll just have a look and see if they have some questions to answer. We have one comment here that says sweet, so I'll take that as being a compliment, but not much of a question. One thing that gets asked, and perhaps James can answer the first one here, is what is the ongoing development plans to some of these options? So I might throw you to James so he can talk about what we're thinking in the future for the pit splitter option.
I think at this stage, initially we're looking at opening it up away from grids to also incorporate triangulations into your horizons. So we're just looking at streamlining it, the process even further. But I'd like to add here that we're always open to suggestions. So if there's anything you've seen today that you think, great, but it could do this or this or this, let us know, and we'll try to incorporate all of your suggestions as best we can into future releases. So keep your suggestions coming in, please.
Okay, thanks, James. And in terms of the throw faulting, we have a few ideas for enhancements. One is to let it try and guess the throw for you, similar to what block faulting currently does. And another is to allow you to fully integrate all the points in the actual throw zone of the fault. And finally, one is to give you more control over the sequence of faulting. So this fault cuts this fault, which cuts this fault. So you have a hierarchy of fault sort of generations, if you like, to try and allow you to break your deposit up into an even more geologically realistic output, if you like. Actually, we do have one more question here. One is saying, what else, sort of in general terms, have you done in version 10 stratigraphically? So there are a range of other options I can very quickly talk about. I guess the first important one is that Vulcan 10 is coal log compliant for the geologists out there who want to make databases and coal borehole graphics and all things like that. It's been fully coal logged, so all the necessary database templates and geological dictionary codes and everything have been set up for you. You go to the Vulcan import option and you can see the coal log option there in the menu. So if I quickly go to File, Import, oops, Databases, and if I hit the right databases option, you can see this coal log standard. So that's all been put in there for you. And that also ripples through to things like I said, the graphics generation. We have all the coal borehole patterns predefined, English log generation, all that's been done. Other things we have done is in fixed HD, it's only a relatively small change, but it's very useful, is the ability to define, say you're trying to do horizons that are actually contiguous with each other. You can now define them and say, well, or are these horizons always contiguous, or are they allowed to have gaps interpolated between them? So if you say it's always contiguous, it means fixed HD will never interpolate a gap between those horizons, no matter what sort of surrounding information tells it to do. So it gives you that additional bit of control. And one other one which I'm just getting my head around, I'll show you very quickly because I think it's very cool, is this called the Geological Sculptor. So if I go into a section view, perhaps I can see it better. So you can see we have these faults here, and I've talked about editing and changing the fault throw and quickly regenerating things. In 10, we do have the option to actually get quite creative. So I can use this option and give it a influence radius and edit it, and then physically come and actually drag this where I want it. And it keeps stratigraphically the relative sequence of everything in check. So obviously you wouldn't necessarily do this for your overall modeling, but if you want to come and tweak it. That is a tool that's available to you to actually adjust your model to be exactly where you want it. So just another thing to be aware of in Vulcan 10. We have actually done a fair bit of stratigraphic enhancements in version 10, and of course there's the entire Eureka trial, which has a lot of good stratigraphic tools in there as well. Okay, so if we don't have any more questions at this stage, I think we might call it a day, and I'd just like to thank you again for your time this afternoon. And if you do have any questions, please get onto the support line. Don't forget, we'll be providing the video of this later on. And, again, thank you for your time. Cheers.